Alright, welcome back everybody. In this video we're going to look at a technique known as logarithmic differentiation. And I kind of have you set up here looking at this table to start with. We've already learned two rules for how to find the derivative of something when we have a base raised to an exponent. We've learned the power rule, which we use when we have a base that is variable and an exponent that is constant. That's that rule right there. So something of the form x to the fifth, for instance. We apply the power rule. And then in our last lesson, we learned about how to take the derivative of exponentials, which those are situations where the base is constant and the exponent's variable. There's another situation which we haven't talked about, which is when the base is constant and the exponent's constant. And in that case, if I try to take the derivative of 5 to the third power, 5 to the third is just a constant, and therefore its derivative is 0. So we have those three scenarios taken care of so far. And our fourth scenario here is when we have a base that is variable raised to a power that's variable. And there's a rule we can come up with for this. It's a little complicated. So instead, I recommend that you just use the technique of logarithmic differentiation. That's how we would come up with the rule that we would use anyway. If you can come up with the rule and use the rule, that's fine with me. So here's how logarithmic differentiation works. First, I look at the function and I see, hey, this is a variable base raised to a variable exponent. So I don't have a rule to handle this. So the first thing I'm going to do is take the natural log of both sides of the equation, which gives me natural log of y equals the natural log of x to the cosine of x. And because of natural logarithm properties, I can convert this over into natural log of y equals cosine of x times the natural logarithm of x. So that's the beginning of my logarithmic differentiation. Then I'm just going to take the derivative of this result using implicit differentiation. The derivative of the natural log of y is 1 over y times the derivative of y. And on the right-hand side, I'll use the product rule. We've got cosine times the derivative of the natural log plus the natural log times the derivative of cosine. Okay? And now I'm going to multiply both sides by y. So dy dx is equal to y times the quantity cosine of x over x minus the natural logarithm of x times the sine of x. And now I'm just going to substitute y back in, and I have my derivative. So I put x cosine of x in here, x to the cosine of x in here for y, and there's my derivative. And that's how logarithmic differentiation works. And we can use that in any scenario where we have y being a variable base raised to a variable exponent. So we're going to look at a few examples here in this video and just kind of fire through them very quickly and look at what techniques we would need to use. Example 1. We have a variable base raised to a variable exponent. Logarithmic differentiation is our best approach. We've got natural log of y times the natural log of the quantity 2x to the x plus 2. We can bring the x plus 2 out in front using natural logarithm rules. And then we can take the derivative of this implicitly. We get 1 over y dy dx equals quantity x plus 2 times the derivative of the natural log of 2x, which is 1 over 2x times the derivative of 2x, plus the natural log of 2x times the derivative of x plus 2, which is just 1. And then we'll clean this up and multiply both sides by y. We get dy dx equals y times the quantity x plus 2 over x plus the natural logarithm of 2x. And then we're going to replace y with what it's equal to. So we've got dy dx equals quantity 2x to the x plus 2 times the quantity x plus 2 over x plus the natural log of 2x. And there is our derivative. Look at example 2. We have a variable base, but a constant exponent. So in order to take the derivative of this, all we need to do is apply the power rule. dy dx is equal to the square root of 3 times x to the square root of 3 minus 1. And there is our derivative. Good number 3. We have a constant base raised to a variable exponent, so we're going to use our rule for exponentials. So dy dx equals 1 over ulna I'm sorry. I got way ahead of my brain there. Back the truck up. Alright, how about this? 5 to the x squared minus 4 times the natural log of 5 times the derivative of the inside, which is 2x. And so our derivative is just going to be 2x natural log of 5 times 5 to the x squared minus 4. My brain misfired there for a second. It's early in the morning when I'm recording this. Alright, the next one. We have a variable base and a variable exponent. Logarithmic differentiation is going to be our best approach. Simplifying, we get that natural log of y is equal to x times the natural log of the tangent of x. And we take the derivative, 1 over y dy dx. And then the product rule, x times the derivative of the natural log of the tangent, which is 1 over tangent, times the derivative of tangent, which is secant squared, plus the natural log of the tangent, times the derivative of x, which is 1. So dy dx is going to be equal to y times the quantity x secant squared of x over tangent of x plus the natural log of the tangent of x. And so dy dx is equal to quantity tangent of x to the x power times the quantity x secant squared of x over tangent of x plus the natural log of the tangent of x. And if I wanted to here, I could decompose the secant squared and the tangent of x into sines and cosines and kind of try to simplify that fraction that way. But that's really not our focus here, so I'm just going to leave it as that, especially since I'm out of room. Alright, number 5. Again, we have a variable base raised to a variable power, so we're going to use logarithmic differentiation. And so this turns into natural log of y equals 3x times the natural log of x. And then I'm going to go ahead and take the derivative. Got 1 over y dy dx equals 3x times the derivative of the natural log plus the natural log times the derivative of 3x. And I'm going to clean all this up. We've got y times the quantity 3x over x just becomes 3. And then I'm going to replace y with what it's equal to. That's a really gnarly 3 there. And if I wanted to, I could factor a 3 out of this function as well. Maybe write this as dy dx equals 3 times the quantity 1 plus natural log of x times x to the 3x. Maybe that's a better looking answer. Alright, and our last example, we have a constant base raised to a variable exponent. So we're going to use our exponential rule that dy dx equals 4 to the 3x minus 2 times the natural log of 4 times the derivative of our exponent. And I'll clean this up into 3 natural log of 4 times 4 to the 3x minus 2. We could also use natural logarithm rules to simplify this here, and this would also be an acceptable answer, 6 natural log of 2 times 4 to the 3x minus 2. So either one of those, depending on our focus at the time, I would accept either one of those at this stage. All right, that's the end of the examples from this video. We've busted through those pretty quick, but hopefully you get the general concept. Look at, anytime you have a base raised to a power, look at the base and the power. Which one's constant, or are they both variable? If they're both variable, we want to use logarithmic differentiation. If one of them is a constant, we want to use the rule that we already had, either the power rule or the rule for general exponentials. All right, that's the end of this video, and I'll see you next time. Hopefully you have a great rest of your day.